Hi, in this video, we'll be learning about how we can make pixels with color. So we've seen how images are made up of pixels. Pixels are the tiny little squares, each of which have their own color, that come together in a grid such that when viewed from a distance, the image looks smooth and it looks like it has curves and lines. But it's all made up of those tiny little pixels that are tiny squares with one constant color. So to make an image digital, to represent an image with numbers, an image can really just be represented as a grid of values, where each value encodes the color at that position in the image. It encodes the color for that pixel. So we've seen the very simple system of just 1 bit per pixel. 0 means black and 1 means white. And this is great when we want to make simple black and white images. But what about color? Most of the images we deal with have color. They're more interesting with color. They're prettier. So how exactly can we encode all the different colors we would want to represent as numbers? Well, introducing the RGB color encoding scheme. So the RGB encoding scheme allows us to encode colors as numeric data. And the way it does this is it defines the amount of red, green, and blue light in a pixel. This is where RGB comes from, red, green, blue. The idea here is that any color can be created by combining red, green, and blue light at varying intensities. So if we add together red, green, and blue light, if we have every light together, we get white. If we have none of the lights, we get black. And if we have some combination, we get every color in between. We can see a better representation here as a color picker. So we have the extremes, red, green, and blue, and in between, we have every color in between. And we can darken and lighten this color picker to get all the various brightnesses. And so this is how colors are represented on your computer screen. If you look really closely at any sort of digital display, be it a TV or an LCD screen or a laptop screen, every single digital display is made up of these tiny, tiny pixels, each of which has a red channel, a green channel, and a blue channel. And by shining varying intensity of light through each of these channels, we get a different color for the pixel. When you stand back, you can't actually see these breaks between the colors. It just looks like one constant color for that pixel. So how exactly does this work numerically? How exactly can we give a number for a color with an RGB encoding scheme? Well, the way this works is each pixel gets 3 values. 1 value for red, 1 value for green, and 1 value for blue. And putting those 3 values together makes a color. So if we have 0 for every channel, then we have no light. We have a black pixel. If we have some mix in between, say we had 156 red, 54 green, and 255 blue, that gives us purple. And if we have them all the way up, if we have 255 for every single channel, that's how we get white. We max out each color to its max intensity, and we get a white pixel. So each color channel gets its own value in the range from 0 to 255. This is the minimum and maximum value for any pixel channel, RGB. And this is nice because this means that each color channel can be represented with only 8 bits. 8 zeros encodes a 0, and 8 ones encodes 255. Even better, we can do this with hexadecimal. Then we don't need to type out 8 bits, we only have to type out 2 hexadecimal digits. So 00 base 16 encodes a 0, and FF base 16 encodes a 255. So this is the range for each color channel in the pixel. So let's look at the layers of abstraction for an example color. Here we have a pixel that is purple. And this is the highest level of abstraction for this pixel. We see just a color, and we can use this color in our images. But this color is actually made up of numbers. It's made up of a group of 3 numbers, R, G, and B. So it has a red of 156, a green of 54, and a blue of 255. But inside the computer, it's not really represented as these decimal numbers. It's represented in binary. And so really, we can represent this number as one binary string with 24 bits. So a single color is represented with 24 bits, 8 for red, 8 for green, and 8 for blue. And we can shorten this with hexadecimal, so we have 2 hexadecimal digits for each color. So this one would be 9C36FF. And the way we usually write this is with a hashtag in front. So hashtag 9C36FF, that encodes the color purple. And this is how we'll usually be representing colors when we're typing them out. Hashtag 2 values for R, 2 values for green, and 2 values for blue. So that's for one pixel, but what about for an image? Well, an image is just several pixels put together. So we're going to get a lot more bits. 24 bits per pixel, so an image is going to have a massive number of bits. It's usually on the order of megabits. So let's take a look at this string of binary and see exactly what colors it's actually encoding. So here we have the first pixel. The first 24 bits encodes the first pixel. The first 8 encode the R value, the second 8 encode the G value, and the last 8 encode the B value, red, green, and blue. Can you guess what color this pixel is going to be? If you said red, you would be correct. Red is turned all the way on. There's no green and no blue, so the resulting pixel is just red. What about the next one? What color is this going to be? So this pixel is going to be green, because the green channel is turned all the way on, it has all ones, and the other channels are all the way off. What about the third pixel? Can you figure out what color this pixel would be? So this pixel would be blue. The red channel is all the way off, green channel is all the way off, and the blue channel is all the way on. So this only has blue light. So another way to represent this would be in hexadecimal. So here, the first 2 hexadecimal digits of each pixel represent the red values, the second 2 digits are the green, and the last 2 digits are the blue. So if we were to add a new pixel, FF, what color do you think this would be? Well, this pixel would be white, because every channel is turned all the way on. We put all the light together and it creates white. What if we have 00, 00, 00? What color would this be? So this pixel would be black, because we have no light in any of the channels. All the lights are turned off, so we have a dark pixel. We just have black. So this is how we can add color to our pixels using the RGB encoding scheme. Let's explore this in the editor. So here we're back in our bit interpreter, and now we're interpreting bits as color pixels as opposed to black and white pixels. We can still go back to interpreting as black and white if we want, but this is going to completely change the scheme. Right now, these first 8 bits encode the entire picture because we only have 1 bit per color. So I can change this first one to a 1, and it'll end up turning white. But if we want to interpret as color, it takes a lot more bits to represent a single color. So here, these first 24 bits are encoding black. This next, every channel is on. We have all ones for red, all ones for green, all ones for blue, so that's going to be white. Here only red is on, so that's going to be red. And here only green is on, so this is going to be green. If we ever want to figure out how to make a color that we don't know how to make using bits, we can use this color picker over here. So just dragging this around, you can see what string of bits maps to what color. We can drag this up and down to get various colors, and drag this around to get various brightnesses. So let's try to finish out our image by trying to create every color we can possibly make by turning channels all the way on. So we've made red and green. How can we make blue? Well, blue is going to have the red and green channels turned all the way off, and the blue channel turned all the way on, 255, the maximum value for blue. So we want a 0 for red, a 0 for green, and a 255 for blue, so that's 8 ones. Awesome, so we made blue. Now what if we turn on both red and green? What color is that going to be? Let's see. We'll give red 255, 8 ones. We'll give green 8 ones. And we'll give blue 0. So that made yellow. And that makes sense. If we look between red and green, the color right in between red and green is yellow. We can also switch from binary to hexadecimal, and this is going to make typing a lot easier for us. So here, instead of 8 bits per color channel, we have 2 hexadecimal digits per color channel. So these first 2 encode red, second 2 encode green, last 2 encode blue. So that's why this pixel is red, this pixel is green, this pixel is blue. So we've tried combining red and green. What if we combine green and blue? What color is that going to be? We'll turn red off, green on, blue on. So that made cyan, and that makes sense. Here we see right in between green and blue, we have cyan. And now lastly, let's try combining red and blue. So we'll turn red all the way on, green all the way off, blue all the way on. And we get pink. Awesome, also known as magenta. So this is how we can create color images with the bit interpreter. Now it's your turn.